Welcome to your first opportunity to hear me talk about things from chemistry, and you take down some notes so that in class we can do some work related to this information. Today I'll be talking about periodic trends, and there are going to be very specific trends that you must know about and understand. And specifically, before I start talking about each of those trends on the next slide, I'd like to let you know that all the trends that we will be discussing, you will be learning about, are due to two properties. And so I need to explain those two properties first. The first property is called nuclear charge. Nuclear charge is literally, if you read these two words, nuclear separately and then charge, you will think, that must have something to do with the charge in the nucleus, and that's exactly it. So the nuclear charge is the number of protons in the nucleus. You're probably saying, Miss Scott, why is it the number of protons in the nucleus? Well, because there's only two particles found in the nucleus, the proton and the neutron, but the only one that carries a charge is the proton. If we look at a quick example of this, we could say hydrogen, the element, the number of protons is 1, and therefore the nuclear charge is 1. You could even say 1 plus 1. If I gave you another example, we could pick the next element, and the next element would be helium. And if we look at our periodic table, we understand that the number of protons that helium has is 2, and therefore the nuclear charge of helium is plus 2. Finally, we could pick an element that's a little bit more sophisticated. We could pick aluminum, let's say. And when we pick aluminum, we realize the number of protons is 13, and therefore the nuclear charge is plus 13. Every element has a different nuclear charge, just like every number has a different atomic number, which is the number of protons in the nucleus. The second factor that influences all trends is shielding. Again, when you hear the word shielding, I'm hoping that you're thinking about shields, or you're thinking about protection. And when you think about shields or protections, often you think about like protection being a distance or protection being some barrier. Shielding is literally the number of energy levels between the nucleus and the valence electrons. So I'm going to draw a picture of this, give you a couple examples. The first example I'm going to give you is lithium. And if you have a periodic table in front of you, or you look at one, you'll notice it has 3 protons. Thinking back, it's just for convenience, we know that the first energy level would have 2 electrons. So it's the first energy level and it has 2 electrons. We know we need to place the third electron, and that of course would go into the second energy level. This would be an example with very slight shielding. This would be a low amount of shielding. And the reason it would be a low amount of shielding is because between the nucleus and the valence, there's not much distance, and there's only one layer and not much distance. You're probably saying, well, Miss Scott, how come when that's just a little bit? Well, now we're going to take the example of cesium, and cesium has 55 protons. I'm going to try to draw this. It's going to get very crowded, so think of like rewriting it on another piece of paper, pausing the video if you want to. And so if we talked about the nucleus, and then we talk about the first energy level, we understand there's 2 electrons. If we go to the second energy level, we go 2s2p, we have 8 electrons. If we go to the third level, or the fourth level, and because cesium has 6 energy levels, we'll have a 5th energy level, and then we'll have a 6th energy level, right? We go 2, 8, and this would actually end up being 18 because it's 3s, 3p, and then because the 4s starts, there'll be 10 more, so it'll be 18. When we think of the fourth, because we've started the 6, that means we have the 4s, the 4p, and the 4d. On the 5, we just went through 5s and 5p, so it's 8. And then finally, we've got 1 in the valence. As you can see, there's quite a bit of shielding layers with quite a few electrons and quite a bit of distance. So this would have a large amount of shielding. So here we have a large amount of shielding. For that atom. I hope those 2 concepts make sense. Nuclear charge is the positive charge that pulls inward on the electrons, and shielding is the distribution and layering of the electrons outward from the nucleus. The trends that you will be studying and be expected to understand and be able to answer questions about include atomic size, ionization energy, cation size, anion size, and electronegativity value. Electronegativity value will be one of the last ones we study because it will be the one that comes up again and again and again throughout the entire year. You are welcome to write those down. I am going to be talking about atomic size first. If you ever need to pause, just pause the video, write down what you need to, and then continue. So, let's talk about atomic size. First, I'll give you the definition. Atomic size is how much space the atom takes up, often given in a radius measurement. Here's an example. This is the element nitrogen. And as you can see, nitrogen has an atomic radius of 0.7 angstroms. The unit is very tiny. Angstrom actually means 10 to the negative 10. That's not as important as you understand that size is literally the radius, and then you would be able to calculate the volume or the size of this species. Every time we talk about a trend, we've got to talk about it in terms of group trend. On Monday, I explained what a group was. But just to review, groups run from top to bottom on the periodic table. This group is called alkali metals. Some groups have specific names. In your book, they name all of these. It's just in this area, and this area, and this area, and this area. They really call them things like oxygen group. So, groups are up and down in columns. So, atomic size, as you can see from this illustration, increases if you start at the top and go to the bottom. So you can see lithium, you can see sodium's bigger, you can see potassium's even larger, and so on. You mostly need to know not just what the trend is, but why it is. And the number one reason that they are getting larger is due to shielding. And this is just a reminder that shielding means more energy levels. It means the electrons take up more space. So in your notes, you should say that the group trend for size is that it increases from top to bottom, and it's because there are more energy levels are shielded. You can pause anytime and go back. When we think about the period trend, all the way back in Unit 1, I had you label the periods down this side of the periodic table. This is the first period and represents one energy level from hydrogen to helium. This is the second period, and everything here has two energy levels. So what happens here is pretty much we aren't changing the number of energy levels, so shielding is constant. If you don't have more energy levels, you don't have more layers, therefore the shielding is not the big thing that makes a difference here. As you can see from the illustration that I've been pointing to, atomic size decreases as you go from left to right across the period. The reason this is due to nuclear charge. This right here is really the backbone of what is occurring, and that is that as the nuclear charge increases, it pulls the electrons inward, and that's sort of shrinking the size. So if you could imagine that cesium had 55 protons. Well, barium actually has more protons, and therefore it has more positive charge, and therefore it pulls inward more. If we look all the way over at radon, we would realize that radon has a lot more protons, and that's simply because we've gone through the F and the D for the 4F and the 5D, and radon has 86 protons. That is a significant increase in inward pull, and therefore that particular atom is a lot smaller. Again, you can pause at any time and go back and look over this again and listen to it again. The next trend that was on the list is ionization energy. You will often see me abbreviate ionization energy, a capital I, capital E. Ionization energy is, the definition is, the energy required to remove an electron from an atom. There are book definitions that talk about how this has to be gaseous. So it has to be a single atom. And a lot of times if they're stuck in liquid or solid, there are many atoms touching each other. So once we get a single atom, we can add energy and we will remove an electron. We haven't really talked about this before, but sometimes one electron is removed, and then other times there are more than one. So make sure you have down the definition. If you get into a situation where there's more electrons being removed, for instance, a second electron being removed, it's called the second IE. If you were in a situation where you're removing 3 electrons, it's called the third IE, or ionization energy. This illustration might be worth drawing. Let me explain it to you. This is aluminum when it's neutral. You'll notice it's pretty big. This is aluminum when it has lost 1 electron. You will notice 1 less electron, therefore it's smaller. This illustration is a loss of 2 electrons total. And this last one is a loss of 3 electrons total. This actually will help us understand some things later on. You will notice that every time we remove an electron, this particular atom is no longer called an atom. That's why it's called ionization energy. This is an ion. because the protons no longer, let me put that in a different color, the protons no longer equal the electrons. This is called an ion because the protons do not equal the electrons, and this is called an ion because the protons really don't equal the electrons. If you really wanted to know what's happening here, in this last one, we used to have 13 protons and equal 13 electrons. But because we lost 3 electrons, we are now down to the same nucleus, the same nuclear charge, but 10 electrons. Way more protons, pulling in more, shrinking it to a really small size. Let's get back to what ionization energy means. Ionization energy is going to be a measure of energy. The energy needed to remove an electron. You'll notice in all the notes I do the group trend first, and the group trend, remember, is always from the top to the bottom within that group. For ionization energy decreases as you go from the top to the bottom. So at the top, it's the highest, and at the bottom, it's the lowest ionization energy. This is for the same reason the size gets larger. This is due to shielding. Because if you have more energy levels, it actually takes less energy to remove that valence electron. If I go back and I look at that drawing at the very beginning, you will get this picture, and you will now begin to understand that ionization energy is the energy to remove this electron. And that's going to take more energy than if we're taking it from something where the electron is way out here. This is lower ionization energy in comparison. Okay? Again, you can pause and go back at any point. So back to the group trend. I don't have any actual numbers here, but you can see that ionization energy is less at the bottom, and that's because it's actually, the electrons are further away, so they're easier to remove. Here, the ionization energy is more. That's why we say it decreases going down. Here are some actual numbers to look at. So we're going to look down through the group. And I want you to observe the numbers that are in each of these boxes. 1,113, 520, 496, 419, 403, and so on. You will notice that the energy, and this energy is in kilojoules per something we'll learn about later called a mole. That energy is less in every single column. You come over here, it's 2,372, 2,080, 1,520, 1,351, 1,170, 1,037. So we can clearly see that the energy is less, and that is because of shielding. Less energy required to remove the electron. Some of you have already begun to look at what's going on as you go across. I will go to the next slide to talk about that. So, we just finished talking about the group trend. So now we're going to talk about the period trend. And the period trend So now I'm going to continue to talk about ionization energy, and I'm specifically going to be talking about ionization energy for the period trend. So you remember, of course, that the periods are being across the periodic table, and since we traditionally read left to right, you will notice that the ionization energy increases from left to right across a period. This trend is due to nuclear charge. You will remember that nuclear charge increases going across, and your nuclear charge is number of protons, which pulls the electrons inward, and therefore it takes more ionization energy to remove electron as you go across. This table illustrates that for you. You'll notice sodium is right next to magnesium and aluminum and silicon and phosphorus and sulfur and chlorine and argon. And these numbers are down like this, but what you'll notice is that these are elements number 11, 12, 13, 14, 15, 16, 17, 18. And so you will notice that these numbers are increasing in general as you go across the period. There's more to this table also. You'll notice they talk about the first ionization energy compared to the second ionization energy. And what you'll notice here is that the first ionization energy for sodium is very low. The second one is a huge jump. I wonder why. Maybe next class we can try to figure that out. You'll notice with magnesium, the first ionization energy is 736. The second ionization energy is given as 1,445. And then, if you try to take a third electron from magnesium, is a huge jump. And it's color-coded in a unique way on this table. The bottom line is that you need to remember when you go across, ionization energy increases, and that's due to nuclear charge. The pull for the electrons is greater. If we look at that further analysis, and I should have changed to this one before, you might want to wonder about the yellow shading. What does this shading mean, and what does it show? If we look at that magnesium, like I said before, we have neon 3s2 for magnesium's electron configuration. Magnesium's electron dot diagram is 2 dots. You will notice that the first ionization energy is a certain amount of energy, and when that one electron leaves, there's still one there. It's a 1 plus now. You have to add more energy to remove the second electron, leaving it with only this remaining. After that second electron is removed, the second energy level is now filled, and it would take an enormous amount of energy to remove another electron. So as you can see, the magnesium 2 plus now has a pseudo electron configuration of neon. So this is after the 2 electrons are removed, it has a filled second energy level, and therefore it's stable. If we tried to remove a third electron, that's what this would be, to remove the third electron. It takes a huge amount of energy, 7,730 kilojoules per mole, which you can see is more than 5 times what we had before. To summarize, if you're looking at ionization energy increases across the period, and ionization energy increases at the top of the group. It's going to be the highest, and therefore a lot of students will learn that it increases going up and to the right. I'm going to pause now, and I'm going to actually do the cation trends and anion trends on a separate video.